So today's topic is mostly talking about to use the simulation augmented machine learning to discover the semiconductor physics and defects. So I will apply the machine learning, but in the data generation process, we use something called TCAD, which I will explain more later, and also spice simulation to help to generate data which are not available in experiment. And then we train a machine to help to discover the physics and the defects in the experiment. So I'm Hiu-Yung from the electrical engineering in San Jose State University. Here are the contributors. This is not possible without the contribution from our students at San Jose State University. We also have collaborators from Virginia Tech, USC, and also Novo Crystal Technology, which contributed some of the papers. So I will first give a boring introduction of ourselves, and then I will go to TCAD-Augmented machine learning. I will start with a naive example and to show that how we can use the simulation to generate data, but then the machine trained with this does not have enough knowledge. So I would say it's the kindergartner level. And then we try to find some method to train it so that they are not so arrogant. So maybe they are just like a fifth grader. And later we try to even train them with the autoencoder to make them more knowledgeable, so they become like a college student and eventually like an engineer. And we can even use the TCAD-Augmented machine learning to do inverse design, and they were just like an expert, okay, and followed by conclusions. So my understanding is this one, the talk will be about 60 to 90 minutes. If that is not the case, let me know, or please stop me. So San Jose State U is a university at the Silicon Valley. We have a lot of students. It's a minority serving institute. In electrical engineering, we have around 700 students. And many of our students are hired in the high-tech company in the Silicon Valley. So what is TCAD? TCAD means Technology Computer Aided Design. So what does it mean? Basically, it's a solver, a simulator, which solves the physical equation, like the Poisson equation, or the Maxwell equation, diffusion equation of electrons, holes, right? Or the process equation that simulates how the gate oxide are formed. So basically, it can predict any transistor or any novel transistor like this 3D BJT, bipolar junction transistor, the process simulation, how a transistor is formed in the process fabrication, or even the optical simulation, like how the wave interference, electrical simulation, or even the back end of the line process of a chip, right? So this is very accurate, as long as if you have the correct equation and also the well-calibrated parameter. So you can think of TCAD modeling as something like just like a real physics, except that we need to make it more accurate. So in principle, this can replace all the experiments. So in our team, we have done a lot of TCAD simulation. As you can see, we do the ab initio simulation, which try to simulate the nanowire or the defects in semiconductor from first principle, from atomic orbitals. We also do NEGF or simulations for nanowires, small transistor, up to power device, novel materials, gallium oxide, diamond, or even circuit simulations, package simulation, radiation simulation. So it just covers everything. And this is not possible without the sponsorship from Synopsys, which provide us the TCAD simulation tools. And at the same time, we also have the cryogenic measurement capability. We can measure down to 4.2 Kelvin to characterize the device that can be used for quantum computer interface. Finally, I know this is a quantum computing group. I want to advertise. I do have a book that is Introduction to Quantum Computing. I assume there's not much background knowledge in quantum mechanics and also linear algebra. So this not from an electrical engineer perspective. I share the knowledge or the experience I had when I was learning quantum computing, after which you will be able to understand the algorithm or keep the how the qubit evolved in a in an algorithm like like the Shor's algorithm or Grover's algorithm. I also and this book you should be able to download for free if your institution has a subscription to the Springer link. I also have 2 classes. One is correspond to this book about the algorithm, and other is quantum computing hardware architecture that you can find in YouTube. So feel free to subscribe me. So sorry, after this boring introduction, now I will go to the real topic. The question that we are studying is that in semiconductor, we usually have the defect. Defect is very important. I mean, we really don't want that because they kill the yield of the chips. And for each technology, if you have a high yield or lower yield by a few percent, it can make the semiconductor fab from profitable to losing money. So that's why it's very important to identify the defect. In the past or currently, people analyze the defect mostly by reverse engineering, doing the failure analysis, which is destructive. Like this is a semiconductor chip, they cut it. You need to cut at the right location. And then you look at the SEM, like scanning electronic microscope, or TEM, transmission electronic microscopy, to find out what happened to the transistor, to the contact, and correlates to the failure in your measurement. But naturally, you will think, in a semiconductor fab, which actually I worked for almost a decade, if you have a very experienced engineer, you give them a curve. For example, this is so-called IDVG curve, the drain current versus the gate voltage. And if he or she is very experienced, by looking at the shape, that engineer already can figure out, oh, maybe the leakage is too large due to gate-induced drain leakage. So there might be a lot of defects at the drain region at high bias. And they can even look at this, say there might be a lot of trap causing trap-assisted tunneling. That's why we have a large leakage current. Or here they may say, why the current degrade when we increase the gate voltage? Is it just a regular physics? But probably they will, based on this, an experienced engineer may already guess, oh, maybe there's a gate leakage. The gate oxide is not good. Or maybe the surface is very rough. So we have much lower mobility when we go to high gate bias. So imagine that if I have an engineer work for 1,000 years for 1,000 technology node in a semiconductor fab, I'm pretty sure the engineer can tell us what happened to the fabrication process by just looking at the IV curve or the CV curve, which are not destructive and to the device, to the structure, and also is very fast to measure and to analyze. And that is the idea that why don't we use machine learning for that? So in principle, for example, this is a diode, right? So here plot the current in log scale. So you will see the current is low when it's reverse bias and it is high when it's forward bias. If we have, for example, a simple variation for the thickness of the N region, intrinsic region, and P region, we see that we have different IV curve. Now, if we generate all this data in experiments, which is almost impossible, and then use it to train a machine. And based on this, when we generate this data, we know what are the thickness and doping of this device. Then we train this machine becomes an algorithm. Now, if I have a new experiment, give me this IV, a certain IV curve, I will be able to know what is the structure inside this device, right? So for machine learning people, this is very straightforward. The problem is, where do you get this data? It is almost impossible in experiment that you ask the fab to change the thickness of the N layer to have 1,000 variations, right? And also for defect, thickness may be easy to control, but for defects, it's difficult to control experimentally. And that's why we propose to use TCAD, which is simulation, like what I mentioned earlier. TCAD is a simulator that can simulate the semiconductor device physics. We use it to generate enough data. Here I try to show a technology node. So when it is not mature, they just started developing the technology. They have a lot of defective die because they just started. However, they don't have many wafers. So because of this, the wafer is low. So number of data, defective data, you can use for training is not much. And when the process becomes better and better, we do have more and more dies because we keep producing more wafers and even sell to the customer. But the yield is supposed to be increased. So the defective dies also reduce. So as a result, in the whole lifetime, you don't have a lot of data to train your machine. I mean, defective data. And even if you have the data, remember, in order to know exactly where the defect is, we need to do reverse engineering. And that is very time consuming and very expensive. So as a result, it doesn't work. So we propose to use TCAD to generate enough defective data, right? And similarly, we can use this to study the circuit. And in this case, we don't use TCAD, we use another higher level simulation tool called SPICE, which is used to simulate the circuit. So you can have the SPICE model calibrated well to experiment, and then you try to do some variation in the parameter, for example, the contact resistor, the transistor width, etc. You generate a lot of data, right? And then you train a machine model. And then in the real time, you can measure your wafer and try to put into this model. And then you will tell it what happened to the contact resistance. And you can quickly, this is really quick, maybe it can happen in minutes, to correlate your electrical measurement to some wafer map. For example, the thickness of the thickness of silica. So if you don't understand this, this is mostly a fabrication process that you metallize the source drain contact to reduce the resistance. By comparing the wafer map of your of what you have from the machine learning to the other process wafer map, you will be able to identify where the process has problem and causing a yield issue in your device. Okay, so this is the motivation. So let's start with a naive example that we proposed in 2019 in a simulation conference called CISPAT. It is very naive. I will spend a little bit more time to discuss, but because this forms the foundation to understand what we have done later. Okay, so as I said, we can have a diode. A diode has N region. You can imagine it has a lot of electron. Intrinsic region, pretty insulator, and then a P region. So in this exercise, we try to apply TCAD to generate 2,000 simulation data very fast because it's only 1D. And we vary the thickness from 150 nanometer to 50 nanometer for the N-type and P-type. And then for the intrinsic region, we change it from 5 nanometer to 16 nanometer. And for this 2000 curve, we get this curve. And this is the average of this curve, right? We turn on all the essential models to model the leakage and the forward current. And here just show the pair plots, how they are pretty uniformly generated and independent to each other. So we use this to train a machine. The first thing we've seen is that we actually need to do some data transformation. We need to apply some what we call the domain expertise. Domain expertise is something I want to keep emphasizing in this flow because later we use autoencoder to avoid domain expertise. And this is important. Because in semiconductor, you have different devices, you have different circuits. You cannot train the engineer for every circuit nowadays, and they need to understand what happened immediately, right? But here we do need the domain expertise. So what does it mean? We train the machine with 80% data for training, 20% for validation. This is just basically a freshman machine learning class exercise, right? So we try to predict what the thickness of the intrinsic layer, which is the thickness from here. If we just dump in the data, you see that we cannot predict it well, right? For very thick thickness, you see that it predicts just flat out. The reason is this. Just due to the device physics, you just take it for granted if you don't know that. When your intrinsic layer is very thick, the current, reverse path current is going to be very small. But when it is thick enough, it will just stay at a minimum value because of the tunneling. There is almost no tunneling. When it is very thin, then we can get larger current. So basically, when you have a small thickness, you have large current, then it's much easier for the machine to understand, to learn that, well, if I change the current level, it must correspond to the thickness of the intrinsic layer. But when you go to really low current level, although it's still changing, but it's changing, you see that from 10 to the power negatives to 10 to the power negative 7. Compared to 10 to the power negative 4, this is like 100 to 1000 current level, right? So if you ask a kindergartner to figure out what is the difference between 0.001 and 0.0001 when you give you a linear scale, the kindergartner cannot understand, because the kindergartner will think that they are all very small. Then it will predict that when your T1 is thick, then you are actually all have a low current. And that's why for all this large thickness, it predicts a small thickness. So the first pre-processing is that you do need to take the log level of the current, then you give a good prediction. A very naive example, right? So we then try this on different machine, multi-layer perceptron, linear regression, decision tree, random forest. And we see even just a linear regression will do it very well. Okay, and why is that? We're going to discuss later. But so this point say that actually very often machine learning doesn't need to go to deep learning, deep neural network, right? And in particular, I want to point out that for the intrinsic layer thickness, we can also only take the last data point, -2 volt, or the whole range, okay, or even just the forward bias. It is able to predict well. Here we represent the mean square error. But for the thickness of the n-type, which determine the forward bias, it only affects the forward bias or the positive voltage, right? So if we apply the positive voltage on the whole range of the curve, it predicts well. But if we only apply the negative bias, at which it does not depend on, then you don't predict well. So the main conclusion here is that you need to provide the relevant physics. So again, here we did not do any domain expertise, but you see that if you try to use machine learning to do some prediction, you need to apply the relevant physics, which is very normal, right? If you for a human being, right? You need to give, now you teach the student, you need to give the relevant material if you want the student to learn something, okay? So another example here, this is just the amplification of this part. As you see that if I want to predict the n plus layer thickness, I cannot give it the negative bias, because if I just give negative bias, there's no correlation, so it doesn't learn anything. But if you give the positive bias, it predicts very well. Let's quickly look at another case. So in this case, we change the simulation methodology. We have a fixed thickness, but then we have different doping concentration. right? If you have a higher doping concentration, you have a lower resistance. If you have higher doping concentration in the intrinsic region, you also have a larger leakage current. Now you look at this curve compared to the previous one, we have more features, particularly in the forward bias. You see that it has a 100 time difference in the current. It also has different curvature. So now this one has more information, and let's see if we use it to train a machine, what happened. So first of all, I want to point out that here we try to ask it to predict the doping concentration if we give it a curve like this. Now, you see that if I only give the highest positive voltage, 1.8 volt to 2 volt, it cannot predict the N-type region and P-type region well. That is because both N and P determine the forward bias. So sometimes it can be the P being very conductive, but N is not, right? However, if I give it the whole region, it predicts well. You see that it can predict the N and P. It can really tell us what is the thickness of the N region, what is the thickness of the P region very well. So why is that? If we try to look at the curve, now I have a N and P, but N and P have different dope concentration, right? This is a typo. Actually, N is more heavily doped and P is lightly doped. I just swap them and then I get two curves. You see that they are different. In the 1.8 to 2 volt, they have very similar current. That's why the machine cannot distinguish or cannot learn from that. But if we apply the whole range from 0 to 2 to this machine, then it learns to distinguish N and P. Okay, so again, you need to provide the right information. Right? Can we even predict the intrinsic region? In principle, we can, because the intrinsic region depends lightly on the currents between 0 and 2 volt depends lightly or slightly on the intrinsic region thickness. So if we try to do second order regression, we can get something better. Can we get something even better? No. If I try to use third order polynomial equation, then it actually overfits. We may need more data. Now, so that is the conclusion. But for those who know machine learning, you already know what the problem is, right? But I will talk about that later. But here, I just want to show one thing. The TCAD can provide, or the simulation, provide a very cost-effective way to generate the IV and CV curve, right? We can generate quickly. You cannot do this in experiment. We vary the structure. And we use this to train a machine. It can correlate the electrical characteristic, the IV and CV, to the structure and defect information well. Okay? And also, you cannot learn more than what the data you gave them. Okay? So, however, we are using the TCAD data to predict TCAD data. Would it work for experiment? Okay? I can tell you that it won't for what we are doing. And some of you may already told yourself, actually, there are lots of overfitting. So let's look at another example. In this example, our collaborator fabricated a Schottky barrier diode. If you don't know it well, that is okay. Basically, it is a diode, and we apply it to the gallium oxide, which is an emergent material. This is a diagram. It has a metal here. So the metal has a work function, which will change the characteristic of this device. We also have a drift region with different doping and different depth, which is going to change its resistance, right? And here shows some of the graph. And what we did is this. We try to calibrate our TCAD model to experiment, so we have pretty good calibration. And then we know that in this fabrication process, because it's a novel device and also we deliberately introduce some defect or variation, we know that the work function, the doping, and the thickness, and also the measurement temperature are different. So we use TCAD to generate 150,000 data. Again, this is impossible in experiment. You cannot ask people to have this variation for 150,000 data. It still takes pretty long time, 2 weeks for us to generate. And then we generate the machine model. Then we feed in the experimental data. Remember, we use simulation data to generate the model and then use experimental data to test this model. So let's see what happened. The first thing, just want to tell you that we calibrate it very well. We take all the physics into account. First, we calibrate the fundamental model, what we call the incomplete ionization model, to the literature. And then we calibrate the device to the sum of the experimental data. You see it has very good temperature dependence and leakage. The markers are the experiment, and then the lines are the simulation. So very nice calibration in my opinion. We then use this to build a machine. So what? We put in the current, and then we do generate high order polynomial, and then do linear regression again, right? And here we use domain expertise because we know that the rate of change of the current is going to determine at least the temperature. So we want to help the machine to learn that you need to look at the rate of change, the delta of the current as a function of voltage. Okay, so we apply the domain expertise. So we have very good training, right? So we train it and then let it predict the thickness, the temperature, work function, and doping. And then the testing also perfect. Again, freshman level machine learning. Everything tests very well, okay? Then we apply this to experiment. And now this is a disaster. I just want to tell you that we did do a very good calibration. The experiment is the green one. The red one is the simulation. This one calibration of the data, right? A very good calibration. But now if you look at the prediction, which are the red point, it predicts the thickness to be even 1 meter long, which is supposed to be in the micron order. The temperature can go to almost 0 Kelvin or 1000 Kelvin. The work function is very long. The doping go to 10 to the power 22. The expected range are all in the dash blue line. Okay, so it's completely nonsense. Why is that? So this is because of overfitting. It's just like that. Why we train the TCAD and teach the machine that in this world you will only see this type of curve. But in experiment, because of this tiny noise, the experiment cannot go to this low level. And when the TCAD was trained with, when the machine was trained with all those TCAD data, it was so arrogant, just like a kindergartner. It thinks that in this world, everything needs to go down to zero as zero bias. And when the kindergarten sees something like that, it tries very hard to fit to the model. And the only explanation is that maybe the thickness is 1 meter, maybe the doping, the temperature is 1000 Kelvin. So that is the problem. Now, if you look at the experimental data, they're so noisy. Okay. So what do? What we did is that, how about we let the machine to extract the, to learn the knowledge. So we don't supply any domain expertise. We did not supply the delta neither. We just give the curve as it is. The curve is discretized to different points. We know that all these data are generated by 4 parameters. So we ask it to find the first 4 principal components and then generates the high order polynomials and then do the predictions. Now, if you look at the result, it is very good. Much better, I cannot say very good. The black dots are those predicted by this machine. Remember, we train it with simulation and use it to predict the noisy experiments, and is able to have all of them confined to the right range. We also use it to predict the temperature and work function. It's not very good yet, but at least now we see the trend. This is the experimental temperature, and this is what the predicted by the machine when we use principal component analysis. But there's a compression. The range is 100 Kelvin, but it can only predict 50 Kelvin. Also, for the word function prediction is not very good, right? And we are going to show you, we can make it better later. So in summary, in this paper, we show that if you use principal component analysis, you can obviate the domain expertise requirement, it avoids overfitting. So when people try to develop machine learning, the machine based on simulation data, we need to be very careful. Make sure that that machine is not overfitted by the ideal simulation, okay? And now, by using the PCA, we can use it to predict the experiment, but still not good enough, right? It's still too confident. And most important, did you learn the real physics? But before that, let's look at another approach that is to apply the noise to the data. By applying the noise, as I said earlier, we will make the machine more humble instead of arrogant. So how does it work? So here I show the PIN diode I mentioned earlier, right? I spent a lot of time on that. Now you know that the PIN diode, we have the first set of data, we change the thickness of N, I, and P, but we fix the doping. Then we have a second set, we fix the thickness but change the doping. I also generated another first set with different thickness and we've changed the doping. Now, if I train the first set with the set 1, I mean train a machine using the set 1, of course it predicts very well, right? For the thickness of the intrinsic, the I layer, and the addition of the N layer and the P layer, it predicts very well. That is what we saw in the first presentation, in the earlier presentation, the first paper. Now, if I apply to another set, you can imagine this is just an experiment, right? It has noises completely different from what you train. You see that the prediction is very bad. It can even predict negative thickness, you see, or a thickness that is way too high. It doesn't work because of overfitting. Now, how can we solve this problem? We decide to add some noise to the training set 1. So we add the noise. What does it mean? It's just like the kindergartner. Just now, look at the perfect simulation curve. Once you add the noise, it learns that, wow, actually there's some variation I cannot explain by using the physics I have learned. So it will just be more humble and try not to fit things too well. So you see that when we add the noise, right, this is a larger noise because it has a smaller signal to noise ratio. The prediction is not as good as before. This was the previous prediction. Overfitter, very arrogant. Adding the noise, it is less confident. If we add a smaller noise, of course, it's more confidence, but still it's not perfect. Then we use it to predict the set 1 and set 2 data, right? I won't go into detail, but as is now, you see that it won't give negative thickness or very large thickness. Now, particularly for the mean, they are very close to the mean that was given here when it predicts the thickness. So it does learn something now after you learn add the noise. We do the same thing to the gallium oxide diode I just mentioned. We again add the noise with different level, right? You see that after adding the noise, the simulation curve is no longer perfect, right? But now, if I add, before that, when I don't add noise, right, it is very bad. It can predict very huge temperature or negative temperature. But now, after adding the noise, without any domain expertise, it can give the full range very well. I still use the relative one because there's an offset. Later, I will show an even better one. But now you see that instead of compressing the range, it gives a good prediction. So in summary, by adding the noise, it is even better than the principal component analysis because we keep telling the machine that be humble because they are noise. That there are many parameters you have not seen in the world before. Okay. So now, but can we make it more knowledgeable? Just adding the noise is just to make it more humble, right? Can it learn something? So we decided to use the autoencoder. So what is an autoencoder? Autoencoder is that you give an input. It's just like a neural network. You give an input, then you go through many layers. Here we only show one hidden layer, but you can have many layers. You constrict it so that it becomes only a few parameters to capture the physics. And then at the output, you have the same number of nodes. Your goal is to minimize the difference between the input and output layer. So you see that if I can make them identical, I basically have created encoder and decoder, because here I have 101 data point. I compress it to only 3 data point, right? I mean, I should say vector, a size of 101, and now it become a size of 3. I successfully encoded this curve as 3 parameter. And then I can reproduce this 3 curve from this 3 parameter to this 101 vector, right? So that's why this is called autoencoder. And here we did not teach it anything. We just say that try to train the machine so that input and output are the same. Then naturally, the constrictor hidden layer would have encoded all the information. And it will encode the essential information. So we do this for the PIN diode. So that's what we do. We have 2 autoencoder. One is just put in the linear curve, a linear scale, just whatever the curve it is, and encode it into 3 parameter, which is the thickness of the N, which correspond to the, it is not the thickness, but it corresponds to the hidden space of the thickness of N, P, and I. We do 3 because we know we generate this curve by varying 3 parameters, the thickness of N, I, and P. We also take the log of the curves and then also do another autoencoder. Then we extract this hidden variable, what we call hidden variable. We only have 6 hidden variables, right? Because we compress the curve to 3 of them. Each of them is 3. One of them is just a linear scale, another is log scale. Then we compress to here. Then we do a linear regression against the thickness, because for each curve we know what are the N, I, and P thickness, right? After we build this model, then next time if we have an experimental data, we put in the IV curve, it should be able to tell me what are the thickness of the device. So we do this. So here again, just show the previous result. It gives a very bad prediction if you train with set 1 and ask it to predict set 2, right? And it gives negative thickness or a very large thickness. But if we use this autoencoder thickness layer, now you will see that you predict the intrinsic layer and also the Tn plus Tp very well. Tn and Tp is still cannot predict well because, as I said earlier, Tn and Tp have a similar function in the diode. They all change the resistor in a similar way. So I won't complain too much when it has the result is not too good. But it can predict the thickness of the intrinsic layer and the addition of them very well. The addition peaked at about 400 nanometer. This one, 200 plus 200, is about 400 nanometer. The intrinsic one is 10 nanometer. What we gave is 10 nanometer. So you see that without doing any domain expertise, right, we are able to predict it well by autoencoder. Okay, so autoencoder works very well, does not require domain expertise. The most important thing is it learned the physics. It learned the physics in the latent space through this latent variable. Okay. Now, can we use it to do something even more, or does it really learn? Right. So we try to see if it can be as good as a device expert. So again, here we go back to the Schottky diode example. Now, from here, what we are doing is that we compare one with domain expertise and one without. Domain expertise means that you have taken solid state physics in your senior class, right, in electrical engineer. So you know that in order to extract the temperature and work function of a Schottky diode, what you want to do is to find, for example, I define the current at 1e-6 and see how this curve shifts. Because if it is shifted, the shift obtained amount depends on the work function. Another is to measure the slope of this curve, because I know that the slope depends on the temperature. So as a domain expert, I'm going to extract V0, where's the location of this curve, and also the slope of this curve, and then put into the neural network, and then let it predict the temperature and work function. Again, I train it with the simulation data and use it to predict this noisy experimental data. Right. Another way is this. Let me use the autoencoder. So we also add some Gaussian noise to make it even smarter, more humble, as we discussed earlier. So this autoencoder will take in the noisy simulation curve and then compress it to 2 hidden layers. We do linear regression and then get the work function and temperature. So when you have an experimental curve, you come here, you just come to here directly, and then you will go through this layer and you will predict what is the work function and temperature. Here, just to show you that these are the simulation data, and this is what we have after adding the noise. Now let's look at the result. The black one is with domain expertise. So here you try to predict the work function. You see that it predicts pretty well. If we try to extract the V0 and SS and then we try to predict it, you see it predict pretty well for this very noisy experimental data. Now, if we try to add the domain without domain expertise but use autoencoder with noise, which is the red one, you see that it's not too bad. It's pretty close to the expert. If we look at the temperature prediction, again, bottom is with domain expertise. You see that for temperature 1, temperature 2, temperature 3, it predicts pretty well, right? For the range and also for the also this vertical range, right? If we have domain expertise with noise, it's also pretty good, right? A little bit worse. But in my opinion, it says the first domain expertise is someone who has taken solid state physics or solid device physics in the school for 1 or 2 years. And then you extract the data and train the machine, then you get this. This one is like anyone, even your humanity level taken any physics class, you can still train this machine and get these results. So autoencoder does perform as good as an expert in this case. So let me also show that autoencoder is not just useful for the device, the defect prediction, but also can be used for the circuit. So in this case, we try to create some circuits. Our students are very smart and very careful. That was during the COVID time. We can only use some very low-grade teaching equipment to do the measurement, which is good because we want noisy data. We create inverter. So this inverter, we fix the NMOS, and then we have different number of PMOS. So as a result, you have different number of resistance for the PMOS. And then we try to say, if you give me the output of the inverter measure curve, can you tell me what are the resistance in the device? And at the same time, we add the resistor to here to mimic the contact resistor. If you have a large resistor, it means your inverter is failing. And this is usually what happens in the semiconductor fabrication. Again, you cannot do this in fabrication. No one is willing to change the contact resistor for you in the fabrication for 1,000 variations. And at the same time, they are not able to do that easily and under well-controlled manner. That's why we use this discrete component. So here show the experimental data with different variation of the contact resistor and the number of PMOS. And we do the simulation. We create a lot of data on the right. So we use the same approach. We input the curve and then let it extract the hidden variable, the contact resistance R0 and R1, right? Again, this is autoencoder. We make this, train it so that the output and input are the same. And then the middle one will encode the most important information, R01 and R2. Now you look at the result, you see that whether I have 1, 2, or 3 PMOS in parallel, I can predict R0 and R1 very well. I am predicting those from the experiment. Look at that the experiment is noisy. Not here, sorry. The experiment, right? It's noisy. It's not always 0, always 3 volt, but for simulation, they are. And they have some noisy parts, but it can do this successfully. If we did not use autoencoder, I'm sure it will be overfitted. Does it learn the physics? We try to plot the relationship or the value of the hidden value H0, right, H1, for different cases, whether NP equal 1 or NP equal 2 as a function of the contact resistance. You see that even we have different circuits, they kind of capturing the same shape, right? And this is just plotting the resistance value as a function of the hidden variable. Again, they have very similar shape. So based on this, I think it does capture the underlying physics. Okay, so we know autoencoder can capture the physics. They're as good as a college student in this example. Can it be an expert? What is an expert in semiconductor physics? Is that you can do some inverse design, right? So I give you something, you tell me what the structure has to be. Okay, so let's sorry, I'm a little bit too fast. Not there yet. Here, actually, I try to verify this with a more difficult task. So this is a 3D simulation of so-called FinFET. We try to vary the width, length, and work function, and we use the same method to train it autoencoder, and then correlates the hidden variable to these 3 variables. Right. This is where result is similar. Of course, when I'm showing here, they must be good result. But the main point is that I want to say that we are able to even get good results with only 50 data. So autoencoder, which learn the physics, does not like thousands of data to train. Right. In this case, even with 50 data, we can predict well. Particularly, we can even predict the GM, which is the first derivative of the curve, pretty well. So autoencoder is pretty powerful. Okay. Now go back to inverse design, which I just said. Right. Now autoencoder can be trained with so few data. It even can capture the first derivative. Can we use it for inverse design? Right, so this is a scenario. At the weekend, right, the circuit designer came to the meeting and say that your device sucks. It doesn't work. We need a better device. Can you come up with a diode like this? And the circuit designer just drew this on the board. This is not a simulation, hand-drawn curve. Come up with a design so you can produce this. Right? As an engineer, a device engineer, you need to try many things, spend weeks and months to come up with this device. Can we use machine learning to help us? So what we can do is just use the model we designed earlier. And then we just plug in this hand-drawn curve and ask it to predict what should be the intrinsic layer thickness and also the P-type and N-type thickness. It tells us that it needs to be this. So we try to do this. In principle, you want to fabricate to verify, but we don't have fabrication facility. We just use TCAD to simulate. And you can see that it can achieve the requirement pretty well in terms of leakage and also the on current. And you may say that, hey, the on current is not good. And the reason is very simple. This is just physics. For a silicon-based PIN diode, you cannot have this turn-on voltage, but at the same time to have such a huge current. So that is nothing to bring about, only to blame the designer being too greedy. Okay. Okay, then the circuit designer decided to even randomly draw more curves. So our student drew 12 random curves and say, can your machine come up with a device that can predict this curve? So here show all the results. The blue one are the hand-drawn curve, and then the orange one are the design predicted by the machine, and then we simulate in TCAD. You see, it can particularly capture all the leakage curve, leakage level very well. Okay, and now it also tries to fit the on current as much as possible. However, it clearly tells us that some of the curves are not reasonable for the given system, silicon, right? Most of them are too high, right? So think about this. This is like an expert telling you that what you are asking doesn't work. You cannot have a turn on voltage at this point. At the same time, you have such a huge current, and your curvature are wrong, right? Particularly, I want to point out for this curve HD10, is it HD10? No, it should be HD11, which is not shown here. For HD11, it tries to draw a curve that is shifted really to the left. And this is impossible for silicon because we're using silicon, not germanium or other device. So it failed to predict. It also draws a curve really to the right, which is HD10. You see that it's really to the right. It actually faithfully tries to reproduce the leakage current and the on-state current. But it also tells the engineer, this doesn't work. Because you're using silicon, you cannot have such a large turn-on voltage unless you use a wider band gap. So everything looks very normal, just like an expert. Okay. Finally, I also want to show that besides doing this 1D reverse design, we can also do a 2D reverse design. So here is that we have a 2D transistor, and they have different poly thickness, gate length, junction depth, substrate thickness. And we want to see if we're given an image, can we predict the current? And more importantly, if you give me a current, can I predict what should be the device structure? So we train two autoencoder image. One is for the image, and other is for the current. And then we correlate their hidden variable for full polynomial regression. And here I only want to talk about the red one, inverse design. If you give me a curve, can I predict the image? So again, this is trained by perfect TCAD data, right? But however, how can we test it? We don't have experimental data. So what we did is try to draw some very noisy curve to mimic the experiment, okay? And then we try to let it predict what structure it will be. Then we simulate the structure to see if we can get the same I on and I off. So this is an inverse design, right? You give me an IDVG, say what curve you want, and then you ask me to come up with a device, a structure that can produce this IDVG, right? And how do I verify my structure is correct? I do a TCAD simulation. So this is the results. First of all, if you look at the actual structure we use to produce the original IDVG curve, right? It does follow the trend, right? It follows pretty well the structure it predicted, right? We know that the leakage current really and on current really depends on the distance between the junction. And more importantly is that the predicted on the so-called predicted I off, the actual I off is the request I off, the I off we want, and the predicted I off is the I off generated by the structure you predicted. They correlate very well. Okay, so in summary, it works well. So I think I spent quite a lot of time now. So that is the conclusion, right? We propose to use simulation to augment the machine learning for semiconductor. It can use to discover the defects and also do reverse engineering or inverse design, right? And in order to avoid domain expertise, this is important because we don't want to study new circuit for 2 years or 1 year or 6 months in order to use the machine. We can use the PCA, noise, and autoencoder, where the autoencoder seems to be the best. Yeah. So we do a lot of TCAD simulation. We can also do cryogenic measurement. We always look for collaborations. So that's all for my talk. Thank you very much.